Good afternoon, everyone. So I'm presenting today our work on OLED OPD matrix. In the future, we want to do fluorescence sensing. Let me start a bit on the motivation. So our aim is to realize lab-on-a-foil systems, lab-on-a-chip systems, use microfluidics to process very small quantities of matter, but typically these lab-on-a-chip systems have an external unit, so you have the microfluidics integrated, but the readout unit is an external device. So our idea is that in the long run, we should be able to do a lab-on-a-foil system that is all integrating, also the optical detection unit, the processing and so on, that everything is really on the foil and we can get a very compact system then. So what we are working on, and have been working on for a while already, is integrating organic light-emitting diodes and organic photodetectors onto a single substrate for such lab-on-a-foil systems. We use organic semiconductor materials as they can be monolithically integrated with the whole range of substrates, as we have already heard today. And I'm going to present to you three different kind of rounds we have been doing on the integration. This is already a couple years back where we did a solution processing of 2 OLEDs and 2 OPDs on a substrate. And all of these substrates, this one, and also this one down here, are 2.5 centimeters by 2.5 centimeters. Then in the next one is an evaporated one with the circular OLED design, and then I will present to you our newest results on the matrix design on a flexible foil. Okay, so let's start with this type of device here, which is a solution process device. And we are fabricating our devices at Kiel University in a clean room environment. We have this little evaporation system, and also we process in a glove box if we do the solution processing. So the procedure is as follows. For the solution processed OLED and OPD on a single substrate, and this was glass here, and we used ITO as the anode, so we patterned ITO, then we spin coated this whole transport layer. The super yellow is the organic light emitting diode emission layer. We spin coated that, and as you can see with the solution processing, if you use spin coating, you have covered the whole substrate. So then we added lithium fluoride aluminum as the cathode using a mask, and used a self-masking process that this metal mask here actually protects the OLED underneath. So if we apply an oxygen plasma, we can etch away all of the super yellow, and we may have remaining the super yellow under the metal electrode here. So that way we could structure the spin-coated layers. And then in the next step, you can actually see on purpose here, we left some of the P.PSS as a layer for the organic photodetector. So in the second step, then PCBM P3HT was spin-coated, which is a photodetector material. We again added lithium fluoride aluminum cathode and used the oxygen plasma to etch away all of the remaining material that is not protected by the two electrodes, and this way we could obtain, even though we use solution processing, on a single substrate OLED and OPD devices. And here in this first test, we had just 2 OLEDs and 2 OPDs on a substrate, so the yellow ones are the OLEDs. We operated the OLEDs with a sawtooth, as shown here, voltage, and could measure on the OPDs a current as we would expect, which is just caused by the effect that some of the light from the OLED enters the OPD. We also did refractive index measurements with this. This is not suitable, though, for fluorescence measurements yet, and this is for the simple reason that the OLED emission is, as shown here, longer range than the OPD detection actually is. And we are interested in fluorescence sensing because fluorescence sensing is the most standard optical sensing mechanism for lab-on-a-chip systems. So that's why we want to use an OLED OPD system that can be used for fluorescence sensing. So we went back and did a second design. That's the second design here. And the second design is actually an evaporated design, again, on a glass substrate. And in the second design, we evaporated on ITO electrodes, the ring as shown here, for the OLED material, which uses the deep BVBI as the emitter material, which is blue-greenish, and then we had a detector here made up out of copper phthalocyanine and C60 as the detection material. And you can see now here the ring-shaped OLED and the OPD in the middle here. And this is what the spectral characteristics are. So we have the emission of the OLED in the light blue, that's this curve here. We have the absorbance of the fluorescence dye we matched it to, shown in dark blue here. We also have here in red the emission of the dye that we selected, and in brown, that is this curve here, we have the sensitivity of the OPD in this system. So it matched quite well, but not well enough for fluorescence measurements, because we do have some absorption in this area here. So we did do fluorescence measurements and also published that in this paper down here, demonstrating that this also does not work yet, because we have too much background and we need to suppress more of the background. So we went on and did a third round, and that's what our current status is. And the third round now is using a PET substrate and fabricating a matrix. So on the new devices now, and you can see a photograph here, we used as the emitter material, which is not very well readable here, again the DPVBI doped with 5% of BCZVBI. It's a 20 nanometer emitter material and has a blue emission, as you can see. Again, ITO was used as the anode for both of the devices. We spin-coated P.PSS as a whole transport layer, and then all the other materials are evaporated by thermal evaporation in the vacuum system. And so this is the OLED stack here. This is the OPD stack, again based on the copper phthalocyanine C60 material as active material. So this stack, these two stacks, we now fabricated on PET foil. The PET foil had a thickness of 200 microns, and it has an indium tin oxide layer of 20 nanometers on top. The active area of each of these devices is 1 millimeter by 1 millimeter. So with this masking here, we realized 18 OLEDs and 18 OPDs on a single substrate now. And so with this, we characterized now these devices. And here you can see the spectral characteristics. As they are similar materials, they're quite similar. So this is the OPD characteristic spectrum. This is the OLED characteristic spectrum. And then we characterized also the properties electrically of the OLED here, first of all. So the OLED current as a function of voltage on the PET substrate is shown here. For comparison, we also plot the current voltage characteristic for glass, and you can see that the onset voltage is quite a bit higher, and we think that, or we know that this is due to the fact that we have only 20 nanometers of ITO, while on the glass substrates we have 120 nanometers of ITO, so the serial resistance is a lot higher here for the PET foil than it is for the glass substrate. So that is definitely something that needs to be improved, to use either thicker ITO or to add additional metal for conductivity. And then we characterize the OPDs as well. We characterize these at a positive bias voltage of 0.1 volts. And we basically just did an experiment where we start with a dark environment, and we see an OPD current in the nanoamp range of about 8 nanoamps. And then we turn on the light in the room. So this is just the fluorescent tube room lights. And you can see the switching behavior here. So then the lights are turned off again, the lights are turned on again. What you also see here for these devices is that we get here quite these spikes, and they even build up more, so there are definitely also capacitive effects going on in this matrix, which is also something we need to investigate. But we could show with these experiments here that we have successfully also fabricated the OPDs in the matrix. So, in summary, we fabricated OLEDs and OPDs on a single substrate, and we think that this is a very interesting way of monolithic integration of different devices. Obviously, the alternative is that you fabricate OPDs and OLEDs on separate substrates, as has been done previously, and you can do it on separate foils and laminate these together, and I think we will have to see what turns out better at the end, but we think it's very interesting to try to fabricate everything on one substrate, and here we could show that it is possible with OLEDs and OPDs, and from our experience, the OLEDs are actually, the organic light emitting diodes are the hardest part to get to work basically together with other devices in one fabrication, that you don't destroy the OLEDs when you fabricate the other devices. So in that sense, we were very happy that they worked in this matrix, and it's now time to move on to the fluorescence experiments. We did do first fluorescence measurements. As I already said, we don't have enough suppression of the excitation light because we do have some spectral overlap in this region here. So currently we are pursuing two redesign routes. One is to add an additional filter in the system. The other is to redesign the OPD stack, which in principle is also possible in order to get a more narrow absorption, such that we do not have the direct excitation light. Since for fluorescence detection you need to have orders of magnitude, basically, suppression of the excitation light. And finally, I would like to thank our funding. We're funded by the European Union within the Rolleiflex project. Thank you for your attention.